Hello everyone, good afternoon to all of you. So have you any doubt from the last class? If you revise the notes, have you any doubt? In the last class, I discussed the typical chemical process. So we find that for any industry, you can say the chemical process that is the heart of any industry. After that, I told you what is a chemical reaction, definition of a chemical reaction, different indication for a chemical reaction and different types of chemical reaction. So in the last class, I discussed all about the irreversible and reversible reaction and exo and endothermic reaction. Are you finding it or not? Bolo. Endo and exothermic reaction. Now try to understand that is one more important reaction, that is the autothermal reaction. Autothermal reaction. Autothermal reaction. Again I am telling you, first one classification I told you all about the irreversible and reversible reaction. In this part we discuss various types of reaction, either that is decomposition, either it is the combination reaction, okay, oxidation reaction, reduction reaction, redox reaction, precipitation reaction. Sir, will every endothermic reaction will be reversible? No, means you will not find out any reaction which is irreversible, any endothermic reaction. Yes, for the endo or exo, it is not the compulsory that reaction means all the reaction will be reversible or all the reaction will be irreversible. No. Soeb sir, एक बार वो graph बता दीजिए and what is activation energy. So Soeb, when I will discuss the rate, okay, then this term will introduce all about the rate constant. Then at that time again I will discuss this diagram. Okay, this diagram I will discuss again. Shankar, in the last class what I told you that the reactants, they have its energy in the form of enthalpy. I am saying it as that is the enthalpy at the standard state, okay, H0. For the reactants, just I am writing it as summation of reactants plus, just I am taking it as reference is same, and the maximum potential energy for the activated complex, or you can say it as transition complex, when reactant will cross the barrier. Reactant will cross the barrier. So what will happen? Just I told you in the last class. If you are not finding this point, just understand. So from the reference, just you can take it as from the horizontal, this energy, that is basically the reactants have this energy. Are you finding it or not? So if that is a single reactant, so just I take it as H0 for the reactant A. We have various reactants, so just you will add up the energy, that is the delta HR, plus when this reactant, suppose I am taking that is the reaction is A gives product, that is the B. So obviously the reactant, it has to cross this energy barrier, which I am saying it as the activation energy, which I am saying that is the activation energy. For the EA, you can say that is the activation energy for the forward reaction. After that, what will find out? Activated complex or transition complex. So then what will find out? It is its energy, means the energy of the activated complex, it is very high. It is very high. So at the same time it is highly reactive. So either it will convert into the again reactant or it will convert into the product. So for the product, what we are finding means they have this amount of energy. Okay, if it is B, so just you will take it as the enthalpy of B at the standard state. And what it is, you can say it as it is the threshold energy or the activation energy for the activation energy for the backward reaction. So in this case, can you apply the energy balance? It is your reference and maximum energy. So it's simple, that is for the activated complex or transition complex. So I can write down it as H0 for the reactant A plus activation energy for the forward reaction is equals to HB0 plus activation energy for the backward reaction. Activation energy for the backward reaction. Simple. What we are finding? We are finding it as H0 A or H0 B minus H0 A. That is nothing but that is the difference in enthalpy of product and reactant. If you are finding it as it is negative, then reaction will be exothermic reaction. How much energy will be liberate? So this much amount of energy will be liberate. This much amount of energy that will be liberate, that is delta H. If in this case it is the negative. But try to understand for this case. If I am taking this case, for this case what we are finding, that product have high energy as compared to that is the reactant. So in this case what we are finding, we will find out as Just for this diagram, I am telling you. If you are finding it negative, so that is the exothermic reaction. What you are finding it as if it is positive, so just reaction will be your endothermic reaction. So for this, potential energy versus extent of reaction or reaction coordinate or progress of the reaction diagram, in this case what we are finding, that products have higher energy as compared to the reactants. That is the reactants. Here reactants and products. So this difference what we are finding, just you can see, products minus reactants. So delta H, that is the positive. Final minus initial. Final means enthalpy of the products minus enthalpy of reactants. We are finding it as it is the positive. What it indicate? That reaction is endothermic reaction. So this diagram, this potential energy versus progress of reaction, so this diagram basically is for the endothermic reaction. So delta H is positive. What we are finding means we are taking energy from the outside, because the energy of the reactants, that is very low as compared to the products. So means we are taking the energy from the outside. So just that is change in enthalpy. You can write out as in terms of activation energy. So just that will be your delta H of reaction. What it will be? Simple, that will be your activation energy for the forward reaction minus activation energy for the backward reaction. Simple. Are you getting it? Sir, how we can say in exo as temperature increase K decrease? यार सोएब just introduction है, topic complete नहीं हुए हैं अभी. Okay, just wait for that. As I already told you, in one class you cannot learn everything. Just give me some time. Okay, as we will proceed further, we'll complete the CRE. All your doubt will be clear. So in the last class, I discussed all about the irreversible and reversible reaction, exothermic and endothermic reaction. So exothermic reaction, you will find out as that is also of two types: highly exothermic reaction, or you can say it as mild exothermic reaction. Same endothermic reaction you will find out as highly endothermic, mild endothermic reaction. So if reaction is highly exothermic reaction, so in this case there is need of to remove this energy from the reaction vessel, from the reactor. So it will not be easy task. Are you getting it? Why? Because the heat liberated, that is in the large amount. Mild exothermic reaction, we can easily remove the heat from the reaction vessel with the help of that we are using the jacket around the reactor. Means by the external mean we can easily remove the heat. But for the highly exothermic reaction, means in this case we can't remove all the heat because it is very highly exothermic reaction. So in this case what will happen? That temperature of the reaction or temperature of reaction mixture inside the vessel, that will increase. हाईली एक्जोथर्मिक रिएक्शन के केस में जिस रिएक्शन में liberated heat that is very high, we are not able to remove all the heat. Mild exothermic reaction, simple, we are able to extract all the heat from the reaction vessel. Same endothermic reaction, mild endothermic reaction, we can easily supply the heat from the surrounding. But when heat required for the reaction that is very high, highly endothermic reaction, okay, so it will be difficult to supply the heat in this large amount for the reaction vessel. Okay, so we will discuss all these reactions later. Some reactions, they will be highly exothermic reaction, some reaction will be mild exothermic reaction. After that I want to discuss third one type, that is catalytic and non-catalytic reaction. Catalytic, you can say non-catalytic reaction. Catalytic, non-catalytic, you can say it as means I was discussing, that was first of all autothermal reaction. Try to understand autothermal reaction. Just understand all about the autothermal reaction. I told you endothermic, exothermic reaction. Autothermal reaction means, for example, just try to understand. For example, just I am taking it as reforming of natural gas. Reforming of natural gas. that is in short form Ng. Natural gas means that all about 94-95% it contains the methane, CH4. It contains the methane. So reforming of methane, that is CH4 react with steam, H2O. Reaction is reversible reaction, produce CO, carbon monoxide plus 3H2. This reaction used at very large scale in all the petrochemical industry or in petroleum industry. So that is basically also that is also called as steam methane reforming. Steam methane reforming means SMR reaction. We say it as SMR reaction. Steam methane reforming. So it is converted into the synthesis gas. What is the synthesis gas? That is the variable mixture of carbon monoxide and hydrogen. That is called as synthesis gas. So that is the synthesis gas. SN means synthesis gas. This reaction, that is highly endothermic reaction. This reaction is highly endothermic reaction. Highly endothermic reaction. So ultimate, from this reaction what we are doing? We are producing the hydrogen. Why there is the need of hydrogen? Because in either crude oil or in refined products we have the sulfur content. Because sulfur, that is the oleophilic impurity. We have the nitrogen compound, we have the oxygen compounds. So this hydrogen easily react with sulfur, produce H2S and other sulfur compounds. With nitrogen produce ammonia and other compounds, reacts with oxygen, produce other compounds. So means with the help of the hydrogen we can purify the finished products. For example, if we have, that is the diesel, okay, we have the petrol. So before selling into the chemical market, there is need to remove out sulfur. So due to that we can maintain the sulfur content as per the permissible limit. For that there is the need of the hydrogen. So in all the refinery you will find out as hydrogen generation unit, and at least you will find out as two plant. Hydrogen generation unit first, HGU second, hydrogen generation unit second. So in this case what we are doing, just we are producing the hydrogen with the help of the hydrocarbon, that is the natural gas, that is the CH4. So in this case what we are finding? Carbon monoxide plus hydrogen, and catalyst used, that is the nickel. Carbon monoxide react with water, produced, what it produce? CO2 plus H2. What it is? That is water gas shift reaction. Ultimate, with the help of this reaction, what is our target? That CO, that is the pollutant. That is the pollutant. So again we want to convert this CO into the CO2. This CO2 we can easily absorb. And the CO means that is also pollutant, CO2 is also pollutant. But what we are finding, with the help of CO, when it will react with H2O, water, so we are finding that H2, so the yield of the hydrogen, that will be increased. This reaction, that is exothermic reaction, but it is a slightly exothermic. It is slightly exothermic, as I told you, that is the mild exothermic. It is highly endothermic reaction. Are you getting it? Slight exothermic. So overall reaction, what is this overall reaction? This overall reaction, that is endo. Overall reaction, if I will say overall reaction, that is endo. Overall reaction, that is the endo. So for that endothermic reaction there is need of energy from the outside. So in this case what basically we do, this reaction takes place in the shift reactor. In the shift reactor, in the top section of reactor, in this top section, Okay, just that is all about the design of the reformer. In the top section, we just burn the CH4 in some amount. CH4 we just burn in the top section. What it will do? It will liberate the heat. This heat I will use for this first one reaction because it is highly endothermic reaction. Highly endothermic reaction. Because here there will be the catalyst, okay, nickel, that is filled in tubes. That is filled in tubes. This nickel catalyst. So this reaction, first one reaction, that is the SMR reaction, will takes place in the bottom part. In the top part, what will happen? In the top part of the reformer, this CH4, that is the fuel, will burn, will generate the heat. That heat we will use for the first one reaction. So due to that, what I am saying, autothermal, there is no need of energy from the outside. There is no need of energy from the outside. So means in this case, we are just conserve the energy by burning this CH4 in some amount. The heat will be liberate. That heat I am using for my reaction. So due to that I am saying it as autothermal reaction. Are you finding it? So there are 2 or 3 important points to understand from this particular example. What is SMR reaction? What is the raw material? Catalyst reaction is highly endothermic reaction. Main product, that is the H2. Second one, water shift gas reaction or water gas shift reaction. CO plus H2O, because water gas, that is nothing but that is CO plus H2, that is called as water gas. Okay, in this case gas and water, we are shifting it or we are converting CO into CO2 plus just the yield of the hydrogen, that will be high. Why this reaction is used in the petroleum industry? Just to remove out the sulfur content from the crude oil, from the finished product, to remove out the nitrogen compound, to remove out the oxygen compounds, because these are oleophilic impurities in the crude oil. Okay, so this overall reaction is endothermic reaction. So I already told you, for the endothermic reaction, what we will do? Just we will supply the energy from the outside to make it feasible. In this case, you can easily understand what we are finding. CH4, methane, CH4, that is the methane. You can understand in this manner. A plus B gives, that is the R plus S, you can say. R plus B again producing, that is T plus S. T plus S. Are you finding? This reaction is A gives R, or you can say A gives R, then R is converting, R is giving, A gives R gives T. So means in these reactions you will find out the, or these can means this can be the example of series reaction, all about the parallel reaction. B, that is producing the S, means R and S, B is producing, that is the T and S. That is all about the competitive reaction. So when later I will discuss all about this series reaction, A gives R gives S. So just this type of reaction you will find out in industry. So for that reaction we will understand all about the kinetics. Okay, how the concentration of A will vary, how the concentration of R will vary, how the concentration of S will vary with time. Okay, so the series reaction and parallel reactions you will find out as, because we have various reactions. Some reactions will be series reactions, some reactions will be irreversible. With irreversible, it may be autocatalytic, it may be catalytic, it may be endothermic, exothermic, because just it is not the compulsion. If any reaction is irreversible, so just it will be irreversible. It may be exothermic, endothermic, it may be catalytic, non-catalytic too. Are you finding this point? So that is all about, sir, सारे endothermic reaction autothermal होते हैं. Autothermal means in this case just by burning the fuel, I will design the reformer in this manner, that is autothermal reformer, ATR, in this manner that I am not taking energy from the other sources. Within my unit, okay, within my reformer, I am taking this energy by burning the fuel. So due to that I am saying it as autothermal. All the endothermic reactions are not autothermal reaction. Endothermic is different, exothermic is different, autothermal means just we are taking the energy from that same unit for my reaction, for my endothermic reaction. Yeah, reformer, that is also the reactor. Reformer, that is also the reactor. You will find out as high temperature water gas shift reactor, low temperature water gas shift reactor. Pre-reformer, in the pre-reformer reaction is also taking place. Just reactor doesn't mean that reaction will take place. In the reformer, reaction will also take place. So for the understanding this reaction, that will be quite complex. It will not be so easy. First one reaction is reversible reaction. Second one reaction is reversible reaction. After that, understand all about the catalytic and non-catalytic reaction. Non-catalytic reaction. After that, you already know autocatalytic reaction. Autocatalytic reaction. You should know all about the photocatalytic reaction. Photocatalytic reaction. Photocatalytic reaction. Catalytic reaction, the reaction in which we are using the catalyst. That is the catalytic reaction, simple. Okay? You have various examples for the catalytic reaction. Catalyst may present either in solid form. Catalyst may present either in liquid form. Catalyst may present either in the gas form. So that is all about the catalyst. Catalyst, you can say it as it is the foreign substance. It is the foreign substance that is neither consumed in the reaction. That is neither consumed in the reaction. But what it will do? It will increase the rate of reaction by providing the surface area for the reaction, by decreasing the activation energy of the reaction, by decreasing the threshold energy of the reaction. First one reaction, that is the endothermic reaction. Second one, that is the exothermic, slightly exothermic reaction. So in this overall reaction, what is the need? There is the need to take the energy from the outside. होगी कि नहीं होगी? तो वो एनर्जी किसी दूसरे प्लांट से या किसी अदर प्रोसेस फ्लूइड से आप नहीं ले रहे हैं. Just you have the fuel. Methane is the fuel. By burning this methane in the same unit, so it is not so easy to design that reformer that in the top section you are burning the fuel, in the bottom section, because ultimate my target that is not to burn the CH4. My target is to just reform it into the form of hydrogen. So from this top section I will take that energy, I will take that heat in the same unit. So due to that I am saying it as autothermal. Autothermal, as the name suggests, auto means khud se, thermal means just that is taking the heat. So there is no need to take the heat from the outside or from other sources. Are you getting it or not? All about the catalyst, what it will do? It will decrease the threshold energy for the reactant, for the forward reaction. Non-catalytic reaction, the reaction in which we are not using the catalyst. That is the non-catalytic reaction. Simple, try to understand. Suppose mostly gas phase reactions. Mostly gas phase reactions. Mostly gas phase reactions. Just I am not saying that when you are finding gas phase reactions, so there is no need of catalyst. Okay. Production of ammonia, we are using the catalyst. That is the iron oxide. But just I am saying it as mostly gas phase reaction. There is no need of catalyst. Why? Because in the gas phase, reactants are easily available for the reaction. Suppose A is in the gas phase, B is in the gas phase, gives, that is the product. So the molecule, you can say the atoms of A and B are easily available for the collision. So when they will collide, bonds will break. After that, they will form the new chemical substance. And it is not the compulsion that all the collisions will convert into the product. So that point means that is all about the collision, breaking the bonds. I will tell you later in detail, but just here try to understand. In the gas phase reactions, the speed, the rate of this reaction, that is already fast. So there is no need of the catalyst. There is no need of catalyst, because some reactions you will find out as completed in seconds. 1 second, 2 seconds, 3 seconds. Some reaction that takes all about 3 year, 4 year, 5 year. These reactions are so slow. We want that the crude oil convert into the petroleum products. This reaction should be so fast that in the fraction of second this crude oil is converted into the finished product or petroleum products. Positive catalyst decrease the activation energy by providing the alternative path, as I told you in the last class. Okay, because we have the positive catalyst, negative catalyst. Same in the biological reaction, we say it as the enzyme. Enzyme, that is the protein basically. What it is? That is behave like as a catalyst for the biological reactions. Inhibitors, so just it decrease the rate of the reaction. In biological process or biological reaction, enzyme, that is behave like as a catalyst. So when the completion time for the reaction that is large, in this case we will prefer the catalyst. The reactions, in this case reactants are easily available for the reaction, so there is no need of catalyst. Okay, they will collide, bonds will break, after that new bonds will be formed. Okay, new chemical substance will be formed. So easily we are finding the product. Okay, so mostly gas phase reactions we will not prefer, that is the catalyst. After that question arises, that is autocatalytic reaction. In this case what will happen? Suppose A gives product, that is the B. This product, that is behave like as a catalyst, so it will increase the production of more B, that is B plus B, or you can say it as 2B. So one of the product behave like as a catalyst. Such type of reaction is called as autocatalytic reaction. All about the photocatalytic reaction. In this case, sunlight behave like as a catalyst, means sunlight simply increase the rate of the reaction. Are you finding it or not? Such reactions are called as, you can say photosynthesis, you can say the photocatalytic reaction. The catalyst generally we prefer for the photocatalytic reaction, means titanium oxide, zinc sulfide, cadmium sulfide. So these catalysts we can prefer in photocatalytic reactions. So either prefer these catalysts, or either in presence of the sunlight the reactant will convert into the product. So try to understand again, catalytic, there is need of the catalyst. Okay, later I will discuss in detail that what is the work of the catalyst in any reaction, because it will not be consumed in any reaction, neither it is participating in any chemical reaction. But what it is doing, it is just providing the alternative path for the reactants. So after that they will cross the threshold energy barrier or activation energy barrier, and they will easily convert into the product. So obviously in this case what will happen? The rate of disappearance of the reactant, that will decrease, that will increase. Rate of production or formation of the product, that will increase. If for any reaction, try to understand, conversion, that is the 80%. Conversion is 80%. So if you are taking the 100 mole of the reactant, so the moles of reactant A will convert, that is the 80%. But these 80%, that will convert fast. Just it will not, catalyst will not increase the conversion. Are you getting it? If conversion is 80%, so it will be 80%. But without catalyst, if it is taking 2 minutes, with catalyst, same 80% conversion can complete in the minutes or in second, 1 minute, or you can say it as less than 1 minute. Non-catalytic, I already told you. Autocatalytic, one of the product, because it is not the compulsion that only one product will be formed. In all the products, one product behave like as a catalyst. Such type of reaction is called as autocatalytic reaction. In this case, what we are doing? Same autothermal. One of the catalyst, means one of the product, that is behave like as a catalyst. So means there is no need of foreign substance from the outside. Within the reaction, what we are finding? That catalyst. So such type of reaction is called as autocatalytic reaction. Only product, not reactant. Photocatalytic reaction, sunlight behave like as a catalyst. Now just try to understand all about the homogeneous and heterogeneous reaction. Homogeneous and heterogeneous reaction. Tell me, that what is homogeneous reaction, what is heterogeneous reaction. What is homogeneous reaction? You can write down when reactant and products are in the same phase, such reactions are called as homogeneous reaction. The reaction in which reactants are and products are present in more than one phase are called as heterogeneous reactions. Are called as heterogeneous reactions. When phase of both reactant and product is same, good, is called as homogeneous. Or you can say homogeneous reaction occurs in the same phase, heterogeneous reaction occurs in different phase. Good. Occurs in more than one phase. Now, a reaction which involves single phase is homogeneous. Reaction involves more than one phase, that is heterogeneous. Good. You can write down in your own language. Now try to understand. Try to understand. First of all, homogeneous, again it can be homogeneous catalytic reaction, non-homogeneous catalytic reaction, homogeneous non-catalytic reaction, homogeneous non-catalytic reaction, heterogeneous, so heterogeneous catalytic reaction, heterogeneous catalytic reaction, heterogeneous non-catalytic reaction. Now try to understand, also catalyst should be in the same phase for homogeneous. Okay. Now try to understand. So means catalyst, we are involved in these reactions, that is the homogeneous and heterogeneous. Try to understand. Homogeneous, as you say, sir, when reaction occurs in the same phase, I will say it as homogeneous reaction. So this definition is correct. Just you will add one more point in this definition. What is that point? When molecules of the reactants are easily available, when molecules of the reactants are easily available for the reaction, that reaction is called as homogeneous reaction. When reactant molecules are easily available for the reaction, now try to understand what does it mean. Means suppose I am taking it as, that is the gas and gas phase reaction. Gas and gas phase reaction. Gas and gas phase reaction. Gas phase reactions. In this case means both of the reactants are in the gas phase. It means, as you already know, that solid has a fixed shape, liquid that will attain the shape of the vessel. Same case, gas, when you will fill in any vessel, so that will attain or that will gain the shape of that vessel. So gaseous molecules means the reactants, they are easily available for the reaction. So gas reaction, that is the homogeneous reaction. Liquid reaction, that is also homogeneous reaction, because molecules of the liquid means reactant molecules, they are easily available for the reaction. But for solid and solid, just you put one solid here, put another solid here, okay, just near to that, after that reaction is not possible, because molecules are not easily available for the reaction. They will not reach to each other. In case of the gas, okay, just fill two gases, after that the molecules, they will be collide to each other, after that will form the product. Two liquid, just put it in a vessel, after that what you are finding? You are finding it as they will be easily available for the reaction, their molecules, they will be collide, and after that product will be formed. But it is not for the solid condition. When reactants are in the solid phase, reactant A, reactant B are in the solid phase, and you are finding that is the product is also in solid phase, but after that it is not the homogeneous reaction. So same phase doesn't mean that means the reactant product, they are in the same phase. It means that reactants molecules are easily available for the reaction. So when reactants molecules are easily available for the reaction, so means that will be the gas, liquid. Okay. Are you finding it or not? So such reactions we say it as the homogeneous reactions. Homogeneous may be homogeneous catalytic reaction, homogeneous non-catalytic reaction. Homogeneous non-catalytic reaction, we are not using the catalyst. Homogeneous catalytic reaction, what we are doing? We are using the catalyst. We are using the catalyst. You will find out as various examples. Means suppose I am taking it as the gas phase reaction. In this case, generally for the gas phase reactions, mostly gas phase reactions, we don't use the catalyst. But it is not the compulsion, as I already told you. Production of ammonia, we use the catalyst. Carbonylation of the methanol, we use the catalyst. And the catalyst which we are using, that is in the gas phase. Just try to understand. Suppose I am taking that is carbon, solid. So in this case, what will happen? In case of the carbon, just when you will put it into the atmosphere, so there is the oxygen that will try to reach at the surface of the solid. Without reaching, means when this oxygen will not reach at the solid surface, at the carbon surface, reaction cannot take place, because reactant is not easily available for the reaction when it will reach at the surface. So around the carbon, what you will find out as that there will be air film. After that, what will happen? Means that air will cross this air film and will reach at the surface of the carbon. Then reaction will take place. C plus O2 gives CO2. Okay, and heat will be liberated. After that, the S content, after burning the coal, after burning the carbon, S content, it will cover the surface of the coal. Then reaction cannot take place until and unless when the oxygen penetrate. Oxygen penetrate means just penetrate from this film. After that, penetrate from the S, then reach at the surface of the unreacted coal. Then reaction will take place. C plus O2 gives CO2. So here what you are finding, that reactant is not easily available for the reaction. Reactant is not easily available for the reaction. Due to that, what I am saying it as when reaction does not occur in single phase, I will say it as heterogeneous reaction. So you can say it as it is your heterogeneous reaction. C solid plus O2 in the gas phase gives CO2, that is in the gas phase, that is your heterogeneous reaction, and it is heterogeneous non-catalytic reaction, because for this reaction there is no need of catalyst. Are you finding it or not? Harsa, how does the product affect if reactants are easily available or not? So in this case, with reaction, physical changes will also take place. That is the mass transfer, heat transfer. So they will also plays an important role. Mass transfer, heat transfer. In this case, mass transfer is playing an important role. Why? Because oxygen that is diffusing at the surface of the coal, it will not diffuse, reaction will not take place. So reaction that is taking place, but in this case what we are finding, mass transfer, first it will diffuse, then reaction will take place. So physical changes, because mass transfer, that is the physical changes, it is diffusing. So in this case, with chemical changes, physical changes will also plays the important role. So obviously the production of the product does not depend on the chemical reaction, but on the physical changes as well. In case of the homogeneous reaction, just reaction means the product, its yield, you can say it as only depends on, that is all about the chemical reaction, because in this case reactants molecules are easily available for the reaction. So homogeneous catalytic reaction, what you will find out, suppose I am taking the example, for example homogeneous catalytic reaction. I am taking it as ethanol. Ethanol in the liquid phase plus ethanol is in the liquid phase plus acetic acid CH3COOH is in the liquid phase. Convert into the ester, and we are using that is the acid catalyst, you can say, which is in the liquid phase. What it will form? It will form that is CH3COOC2H5 plus S2O. Means this ester is in the liquid phase, water is in the liquid phase. You can say this is the example of homogeneous catalytic reaction. Homogeneous catalytic reaction. In this case, what we are finding? Reactants are easily available for the reaction. To increase its rate, we are using the catalyst. So all are in the same phase. Are you finding its meaning? That homogeneous reaction occurs in one phase, in single phase. That product will be liquid. Water means that is already the liquid. And as far as the catalyst is concerned, it may be in solid phase, catalyst may be in liquid phase, catalyst may be in gas phase. Carbonylation of methanol, okay, that is basically called as Monsanto process. In that process, the catalyst we used, that is in the gas phase, that is the rhodium catalyst. So you will find out as that there will be the catalyst cycle, okay, and that will be in the gas phase in this case. Obviously its rate will be so slow that you can say that reaction is not occurring. Aniket, Monsanto process, that is the carbonylation of the methanol. So what will be formed? Acetic acid will form. In this case, the catalyst used is in the gas phase. Okay, that is the rhodium based catalyst, but that will be in the gas phase. Homogeneous non-catalytic reaction, mostly gas phase reactions. You will find out as comes in the category of homogeneous non-catalytic reaction. Heterogeneous catalytic reaction. Heterogeneous catalytic reaction. In this case, you can take it as the example of production of ammonia. Production of ammonia. Production of ammonia. You will say, sir, production of ammonia, nitrogen and hydrogen are easily available for the reaction, but their rate is very slow without catalyst. And catalyst is in the solid phase. Okay, so due to that, when the reactants will reach at the surface of the catalyst, then reaction will occur. Its rate will increase. So due to that, production of ammonia, that is the example of heterogeneous catalytic reaction. Other than that, sulfur dioxide convert into sulfur trioxide by reversible reaction. Reaction is exothermic reaction. In contact process in the production of sulfuric acid, we prefer the platinum as a catalyst or vanadium pentoxide. Platinum or either vanadium pentoxide is in the solid phase. That is the example of heterogeneous reaction. That is the example of heterogeneous reaction. You will find out if you will see one more example. Production of sulfur trioxide. So that is in contact process. The catalyst used, that is the platinum or vanadium pentoxide. Currently we prefer that is the vanadium pentoxide because platinum, it is very costly. Is in the case when I am producing the sulfur trioxide with the help of sulfur dioxide and oxygen in lead chamber process. In lead chamber process. In this case, we use the catalyst, that is nitric oxide, which is in the gas phase. You can say it is the example of homogeneous catalytic reaction. Homogeneous catalytic reaction. So just you will find out as that there are not just one or two examples in which catalyst will find in the gaseous phase. Okay, there are lots of examples. So catalyst can present in solid phase, most of the time in solid phase. It may present in the liquid phase. Sarthak sir, all are in gas phase. So how it is? Sarthak, you are talking all about this sulfur trioxide. That is in the solid phase. V2O5, that is in the solid phase. For this example, that is the example of homogeneous catalytic reaction. I am telling you. नहीं, याद नहीं करने पड़ेंगे, जस्ट आपको समझ में तो आनी चाहिए ना कि उसके पीछे कॉन्सेप्ट क्या है। भाई अल्टीमेट ऐसा तो है नहीं कि आप रिएक्शन से बस जाओगे, आपको एसएमआर रिएक्शन के बारे में नहीं मालूम होना चाहिए, वाटर गैस शिफ्ट रिएक्शन के बारे में नहीं मालूम होना चाहिए, तो ऐसा तो नहीं है ना। वो प्लांट्स में, अब सिंपल मैं यहां पे लिखूं ए गिव्स बी प्लस सी, सो ये कोई रिएक्शन ही तो है जो प्लांट में हो रही है। तो आपने पढ़ा होगा कि जस्ट यू थिंक इट एज इट इज द केमिकल इंजीनियरिंग, बट बिहाइंड दैट देयर इज द फुल मूवी। Contact process, lead chamber process, both are used in the production of sulfuric acid, but currently we prefer, or we are using, that is the contact process. Okay, that is, you can say it as obsolete. Okay, it is used previous, but currently we are preferring, that is the contact process. हाँ, DCDA process बोलते हैं, डबल कॉन्टैक्ट डबल एब्जॉर्प्शन प्रोसेस। हाँ जी बिल्कुल, पाउडर में मैं तभी तो बोल रहा हूँ ना कि मैं सॉलिड फॉर्म में, यू कैन से इट एज इन द पाउडर फॉर्म, ऑब्वियसली पाउडर फॉर्म में भी यूज होता है। गजनी मत बनो, नहीं मालूम चले वो इंटरवल, वो एग्जाम में याद है जो 15-15 मिनट वाला इंटरवल है ना। सो दैट इज ऑल अबाउट दी heterogeneous catalytic reaction. Heterogeneous non-catalytic reaction. Heterogeneous non-catalytic reaction you will find out as rusting of iron, corrosion. Simple, these are the example of heterogeneous non-catalytic reaction, because iron, that is, you can say iron article, in starting it is very shiny form, but after that its color change, it's become reddish brown. Okay, so just this iron that will react with humid air. Okay, when this the humid air will come in the contact of iron, what will happen? It will be react, and just you can say here you will find out as the color change, as I already told you in the last class, that when you bite or cut the apple, so that is the indication that reaction can takes place, color change. So in a rusting of iron, color will change. So obviously this is the, means here the reaction can takes place, and surely there is the reaction, because this shiny article of iron, okay, it will convert into reddish brown, okay, and after some time what you will find out as, when there is the continuously rusting on the iron, that iron article that will be simple collapsed. हाँ जी, V2O5 यूज करते हैं, वेनेडियम पेंटॉक्साइड, इन द प्रोडक्शन ऑफ सल्फ्यूरिक एसिड इन कॉन्टैक्ट प्रोसेस. यूज ए पोल हेयर टू, हाउ मेनी ऑफ अस विल फाइंड डिफिकल्टी टू स्टडी सीटी. यार अगर आप सीआरई में सही से समझोगे तो कुछ पॉइंट्स तो मैं ही याद करवा दूंगा आपको. आप लोग ना तो हार जरूर पहले मान लेते हो. Means you will find out as some advantage of the platinum catalyst, some disadvantage too. At the same time, you will find out as some disadvantages within V2O5, some advantages too. Okay, so सारे factors को consider करके now currently we are using, that is the vanadium pentoxide. एक खाली cost ही सब कुछ नहीं होता है, बाकी सारी चीजें भी होती हैं. वही तो मैं बता रहा हूँ आपको, सारी चीज होती हैं, खाली cost एक factor नहीं होता है. After that, are you finding catalytic, non-catalytic, autocatalytic, photocatalytic, homogeneous, heterogeneous? Any doubt till this point? Are you finding any doubt? सर photocatalytic में सिर्फ सनलाइट के अलावा भी तो मैंने आपको कैटलिस्ट बताए हैं, TiO2, ZNO, ZNS, CDS. सो ये कैटलिस्ट भी हैं जो कि आपके यूज होते हैं. नाउ अंडरस्टैंड, elementary, non-elementary I will discuss later. The reaction based on order, 0 order, first order, second order, I will discuss later. All about the series reaction, parallel reactions, parallel reactions, chain reaction, non-chain reactions. Okay, I will discuss after defining the rate. Okay, then you will easily understand all about the remaining reactions. हाँ, सनलाइट के अलावा भी कैटलिस्ट हो सकते हैं, ठीक है, ऐसा. Now try to understand that what is CRE. What is CRE? Chemical reaction engineering. Remaining reactions I will discuss after defining some certain terms. Okay? Then I will tell you all about the reactions based on the order, based on the molecularity, elementary, non-elementary reactions, series reaction, parallel reaction. So I will discuss later. Just wait for that. Now understand chemical reaction engineering. Chemical reaction engineering. In this subject, what we will discuss? First of all, what I am finding, one point that is all about the stoichiometry. Second one term you should understand, that is all about the chemical kinetics. Just first understand these words, chemical kinetics. Third one, that is all about the chemical kinetics or you can say it as reaction rate. Third one you can say reaction mechanism. So that both comes under the category of chemical kinetics. First of all, you should understand in the CRE what I will did. I will discuss chemical kinetics. Chemical kinetics means that is all about the speed of reaction, rate of reaction, as well as the reaction mechanism. The reaction mechanism means that reaction is taking place in a single step. This means ultimate we are finding it as A gives product, but maybe possible this reactant first of all is converting into the other intermediate, then it is converting into the product. So due to that, in chemical kinetics we will also discuss the reaction mechanism. So first point I can say CRE, that is the study of chemical kinetics means just I will understand what is the rate of the reaction, how fast or slow any reaction can takes place. Are you finding this first one point? That is all about the chemical kinetics. So just I will discuss all about the chemical kinetics. No, along with chemical kinetics what we will do, we will understand the designing of chemical reactors. The designing of chemical reactors for what? For homogeneous reaction, for heterogeneous reaction, for homogeneous reaction, for heterogeneous reactions, for biological reactions, So we will design the reactor. And you know very well, to design any reactor, there is the need of knowledge, information, there is the need of experience, chemical kinetics, and just you can say knowledge from the various areas like heat transfer. You should have the knowledge of heat transfer, mass transfer, FM, thermodynamics, because it is very important subject, thermodynamics. After that you can say that economics, then you can design the reactor. So it is not the easy task. In this subject what we will understand, we will understand all about the chemical kinetics, means the kinetics of the reactions. Along that we will learn how to design a reactor for the homogeneous reaction, heterogeneous reaction. Then reactor may be ideal reactor, non-ideal reactor. Okay, so we will design the reactor. Other than that, we will design the reactor for the enzyme reactions, biological reactions. Kinetics say how rate of reaction change with time, obviously. Now tell me, are you finding what we will study in CRE? Write down, it is the study of chemical kinetics along with chemical kinetics. If someone asks what does mean of the chemical kinetics? Simple, that is nothing but that is the speed or rate of a reaction. Along that reaction mechanism. So we say it as chemical kinetics. Are you getting this point? It is the study of chemical kinetics. Because in the last class, I take the example, I told you, if the speed of my vehicle, that will be more, so obviously to cover the same distance, I will take the less time. And the speed of some other vehicle, that is very high, so obviously it will take less time than me. So just this CRE, by studying of the chemical kinetics, tells us that it is the rate of this reaction. And thermodynamics tells us this is the maximum conversion for this reactant in this reaction. After that, I will try by changing the operating conditions, that to cover the means to sustain the maximum rate. So after that I can attain the equilibrium conversion, I can attain the maximum conversion, because equilibrium conversion, that is the maximum conversion. I cannot convert my reactant into the product beyond the equilibrium conversion. You can say it as this is the limit. This is the limit. So you can write down it as, it is the study of chemical kinetics along with design of chemical reactor, along with design of chemical reactors in which chemical reaction will takes place, in which chemical reaction will takes place, in which chemical reaction will takes place, in which chemical reaction will takes place. So in the CRE we will discuss all these points, all about the chemical kinetics, all about the design of reactors for the chemical reactions. So once we know the speed, we know the rate of any reaction, after that easily we can design. After that easily we can design. So first of all we will discuss the chemical kinetics, then we will design the reactors. Are you getting this point? Now tell me, what is the chemical reactor? What is the chemical reactor? Or simple you can say it as the reactor. What is a reactor? स्टेटमेंट तो मैं रिपीट कर दूंगा, बट आप लोगों को फिर डेफिनेशंस को समझो ना, बाकी अगर ऐसे ही याद करना है तो फिर समझाने का कोई मीनिंग नहीं है. व्हाट आई एम टेलिंग यू, इट इज द स्टडी ऑफ केमिकल काइनेटिक्स, उसकी स्टडी करनी है अलोंग विद द डिजाइन ऑफ केमिकल रिएक्टर्स. उसके अलावा किसकी और स्टडी करनी है? डिजाइन ऑफ केमिकल रिएक्टर इन विच केमिकल रिएक्शन विल टेक्स प्लेस, जिसमें आपकी वो केमिकल रिएक्शन मीन्स दैट केमिकल रिएक्शन विल अकर. सिंपल. व्हाट इज ए केमिकल रिएक्टर? टेल मी फास्ट. गुड हरिकेश. ए वेसल वेयर केमिकल रिएक्शन टेक्स प्लेस. सुकंत, द स्पेस गिवन फॉर द रिएक्शन. राइट डाउन. It is a vessel, it is a vessel or an equipment, it is a vessel or an equipment in which reaction will takes place by maintaining the favorable condition, by maintaining the favorable condition. Good. So it is a vessel or an equipment in which chemical reaction will takes place. Chemical reaction will takes place by maintaining the favorable conditions for the reaction. Now try to understand. This diagram is very important. In the reactant there will be the input, which I am saying it as, that is the raw material which is ready for the reaction. That is the input. That is the input. After that, what we are finding? It is the reactor. So for that reactor, when it will convert into the product, so just there is the need of to understand the kinetics. To understand the kinetics, either it may be the chemical kinetics, that is rate of the reaction, chemical kinetics, or you can say that is physical kinetics. Physical kinetics. Try to understand. For the homogeneous reaction, just there is the need of the chemical kinetics. Chemical kinetics means that the speed or rate of a reaction. Speed or rate of a reaction means how any reactant it disappear, or how any product, what is the rate of formation of any product. So for the homogeneous reaction this is sufficient, but for the heterogeneous reaction, because phase are not easily available for the reactions, so along with chemical kinetics there is the need of the physical kinetics. Physical kinetics means rate of heat transfer, rate of heat transfer, rate of mass transfer, rate of mass transfer. So along with chemical kinetics, that we require the heat transfer and mass transfer. So in homogeneous reaction I will discuss this part all about the chemical kinetics. When we will reach in heterogeneous section, So just along with chemical kinetics, I will take the rate of heat transfer as well as rate of mass transfer to describe the kinetics of that reaction. Are you finding it? So in this vessel there is the need of kinetics. Means to design the reactor, when we want to take place any reaction at favorable conditions, first of all we will see that what is the kinetics of the reaction. Other than that, second one term which is very important, you can write down as that is contacting pattern. That is the contacting pattern. Contacting pattern, it is very important. How it is very important? Because reactants which are reacting, which are contacting, so just they are simple in batch mode. In this case what we will do means, once we fed the reaction mixture in the vessel, so there will be no continuously in, there will be no continuously out. Means they will be contact, they will be reactant, they will be react in batch mode, or either they can react in continuous mode. Continuous mode means, just try to understand, continuous mode means continuously input will occur, continuously output will occur. Continuously input will occur, continuous output will occur. So that is the batch, means there is no input output. When you will, and there is no continuously in and out, that is the batch. Continuous, continuously in, continuously out, that is the basically continuous. This is the meaning of the continuous. But after that, contacting pattern means either in plug flow, either in mixed flow. Plug flow, either in mixed flow. Plug flow or mixed flow. Just again try to understand, we have the input, that is the raw material which is now ready for the reaction. Then it is the vessel, we will maintain the favorable condition. So just to design that vessel, there is the need of to understand first of all what is the kinetics. What is the kinetics of this reaction? So just for the homogeneous we will define the chemical kinetics. For heterogeneous, chemical as well as physical kinetics. Other than that, the reaction mixture is, or the reactants, they are reacting in batch mode or in continuous mode. So you will say, sir, continuous mode. In continuous mode, plug flow and mixed flow. In plug flow and mixed flow, their contacting pattern, their contact to each other is different. And these are the ideal conditions. What you know, in case of the plug flow, the concentration of the reactant in the radial direction, just try to understand, that will be uniform. In radial direction, or I can say it as, in radial direction there is the infinite mixing. In radial direction. Are you getting it or not? In radial direction there is the infinite mixing. So means, in case of the plug flow, here in starting the concentration of the reactant is high. Along the length of the reactor, the concentration of the reactant will decrease, because it will convert into the product. So what we are finding? We are finding it as, when I am taking it as the plug flow condition, that is the ideal condition. Later I will tell you what is the plug flow. It is the ideal condition. Ideal condition means that the reactant molecules, they are reacting in this manner, that in radial direction at any point, either at this section, at this section. In the radial direction, there is no concentration gradient. In radial direction, mixing is infinite. Are you finding this point? And there is the concentration gradient along the length of the reactor. So if reactant are contacting in this manner, so in continuous I will say it as, it is the plug flow condition. Plug flow condition. Mixed flow. Mixed flow, what you are finding? As reactant that is entering at the same time as it is entered, at the same time there will be the uniform mixing or infinite mixing. So what will happen if there is the infinite mixing? So either at that point, concentration that will remain same. Concentration is not the function of the position. At any instant, at any time, concentration inside the reactor is uniform. But after that, as the reactant concentration will decrease, at the next second, concentration of reactant will decrease because it is converting into the product. But at any time, concentration of reactant inside the reactor will be uniform. So that is also the ideal condition. Later I will tell you why it is the ideal condition. Because in non-ideality, you will find out as some reactant that will stick with agitator. So just it does not mix properly. So the concentration of reactant at the agitator is high. So what will happen? That the concentration in other part of the reactor is different. Just the reactant which is at the surface of the blades, here concentration is different, then diffusion will take place. Non-ideality will introduce. So in case of ideal condition, what I am taking it as that concentration surely will decrease at different time, but at any instant concentration in whole reactor will be uniform due to the infinite mixing, due to the uniform mixing. So I am saying it as the mixed flow. Are you finding? So that is the ideal condition. Non-ideal, once you know the ideal, after that we will understand the non-ideal condition. Plug flow, that is the ideal contacting pattern. Mixed flow, that is the ideal contacting pattern. Due to that, in this vessel, this reaction is taking place. I am saying it as MFR. The contacting pattern, that is the plug flow in this reactor. So I am saying it as the PFR. Are you finding it or not? Means there are the various points. In plug flow, you can say it as this plug that will not mix with the plug which is moving forward from that plug. So आपस में कोई interaction नहीं होगा. Each molecules will remain for the same time, for the same duration in the reactor. That is called as the plug flow condition. So that is one of the contacting pattern. That is my point. Are you getting it or not? Mixed flow, in this case what will happen? As the reactant will enter at the same time, there will be the uniform mixing. So there will be no concentration gradient. Means dCA with respect to ds, either in x direction, y direction, z direction, that will equals to 0. There will be no concentration gradient due to uniform mixing. Here in radial direction, there will be no concentration gradient. But in axial direction, there will be a concentration gradient. Are you getting it? Just try to understand. Otherwise, you will easily write down. Hanuman, basically, these are the contacting pattern and these are the ideal pattern for contacting. Due to that, I will say PFR. There is no need to say it as ideal plug flow reactor because individually it is already ideal. So I will say it as the plug flow. Plug flow means, suppose what we'll find out as here concentration of reactant A is high just at the entry. After that concentration will decrease. So here I am saying it as in starting that concentration is 10. Now the concentration is 8. So at this section concentration that is the 8. So concentration along the means in the radial direction, that is the uniform. But in actual condition it is not possible. So due to that, what I am saying it as the ideal flow. I am saying it as the ideal condition. In this case, what I am telling you, means as the reactant will enter, at the same time there will be the uniform mixing, so there will be no concentration gradient in any direction, either x direction, y direction or z direction. So I am saying it as the mixed flow. I am saying it as the mixed flow. But in actual condition, what will happen? What will happen? Means you will find out as some reactant that is not participate, that is not come into the mixing contact. After that, it is directly out. It is stuck with agitator. It is stuck with agitator. After that, it comes out. So these will be non-ideal condition. So just when I will discuss non-ideal reactors, at that time I will tell you. So means for design a reactor, I told you there is the need of information, knowledge, experience, okay, all about the kinetics of the reaction. Other than that, knowledge in various areas like heat transfer, mass transfer, FM, fluid mechanics, economics, then you can design the reactor. Okay, so that is the contacting pattern. Other than that, what we are finding? Contacting pattern, when I will discuss non-ideal reactor, may be possible some reactant molecules react or just mix in very starting, early mixing. After that, they will not mix. They will come out. Means in very starting of the reactor, early mixing. That is the contacting pattern. Means with the help of the contacting pattern, we will understand how early or late the reactant particles will mix. So early mixing, so just at the starting they mix, after that they comes out. Okay, they are mixing with all over the reactor. They are mixing late. In starting they are just coming out, they are not mixing. After that, later they are mixing. The reactant particles or reactant molecules are mixing. That is called as late mixing. It is the early mixing. So contacting pattern, that will tells us all about the mode of the operation, that is the batch or continuous. In the continuous, what is the pattern? Plug flow, mixed flow, and it tells us how early or late the molecules of the reactant will mix. It means the plug flow violates the boundary layer concept. Obviously, that is the highly turbulent flow. Plug flow is nothing but that is the highly turbulent flow. Highly turbulent flow means it's violate the boundary layer condition. Very high Reynolds number, or you can say it as Reynolds number tends to infinite. So then you will get the flat velocity profile. At any section, the velocity of the particles, that will be same, flat velocity profile. So that is ideal condition. Are you getting it or not? Now understand. So just when you will deal with the reactors, at that time what you will find out? You will find out as the design equation or performance equation. Design equation or performance equation. Design equation or performance equation means we will find the design equation or performance equation for the different reactor. For PFR it will be different, for the MFR it will be different, for the batch reactor it will be different. So performance equation or design equation, what it tells? It tells us, or it relates input with output. Input with output, that is called as performance equation. You can write down performance equation relates input with output. Input with output. How it relates? That output which we are finding from the reactor, that will be the function of input. That will be the function of kinetics. That is the function of kinetics and contacting pattern. So means all these factor will affect this output. Means input, it is important. Kinetics means that will tells us all about the rate or speed of any reaction. Contacting pattern means what is the contacting pattern? Means how the molecules of the reactants, they are contacting with each other inside this vessel. After that, we will find out the output. So, the design equation or performance equation for any reactor just relate the input from the output. Input from the output, that is called as design equation or performance equation. When I will discuss all about the design of ideal reactors, at that time again I will tell you in very detail all about the plug flow condition, mixed flow condition. After that you will add out as reactor design uses information. Reactor design uses information. Reactor design uses information, comma, knowledge from different areas, knowledge means reactor design uses information, comma, knowledge from different areas, in bracket chemical kinetics means knowledge of the chemical kinetics, thermodynamics, heat transfer, mass transfer, FM, economics, etc. Chemical means reactor design uses information, knowledge from different areas, bracket chemical kinetics, thermodynamics, heat transfer, mass transfer, fluid mechanics, economics, etc. and vast experience. Okay, so that is all about the chemical reactor. So till this point, if you do not have any doubt, so just I want to start definition of a reaction rate. So just try to understand definition of a reaction rate. Any reaction I am taking, suppose that is A gives B. That is your reactant and that is your product. So at time t is equals to 0, I have the concentration of A, that is your Ca0, and in starting that we do not have the product, so that product is 0. Concentration, simple, you can easily find out. Concentration, that will be concentration of A in very starting, that will be Na0, or just you can write out as at time t is equals to 0. We have the moles of A, that is the Na0, okay, and moles of B, that is 0. So means in starting there is the pure A, in very starting reactant, that is the pure A. After that, at any time t, what will happen? Some moles of the reactant A will disappear or will converted into the product B. Now at that time the present mole of A is Na. Present mole of A is Na, and the moles of B, that is the Nb. Try to understand. Definition of a reaction rate means, suppose we have any reaction, A gives B, reactant A is converting into the product B. So at time t is equals to 0, the reactant is pure A and the moles of reactant A, that is the Na0. When it is the pure, so the product that will not be present, so the moles of the product B, that is the 0. At any time t, reactant A will react into the product B. Now remaining mole, that is the Na. Na is what? Remaining mole of A at time t. Remaining mole of A at any time t. Na0 starting mole. So just we define term that is called as rate of disappearance of A. Rate of disappearance of A. We say it as, or we denote it as minus R. R stands for, that is the rate. For reactant A. This negative y, what I'm means why I am using, because it tells us that is all about the disappearance. That is all about the disappearance. That is all about the disappearance. So rate of disappearance of A. So you know very well how I will write it. I will write out as remaining moles minus starting moles divided by final time minus initial time. Final time minus initial time. Final time minus initial time. So rate of disappearance of A. So means what we are finding, this term is negative, but rate cannot be negative. Can you say, sir, the speed of your vehicle, that is the minus 30 kilometer per hour. So just what we are finding means we will make this rate positive. How will make it positive? Just by multiply with negative sign. That is just by multiply with negative sign. So what it is? That is nothing but that is minus dNA divided by dt. dNA final moles at time t minus initial moles divided by final time, that is the t minus 0. T minus 0. Are you finding it? Otherwise you can write out as final moles, or suppose these are the moles at time t. T1 Na naught at time T2, that is the Na. So what you will write down? You will write out as rate of disappearance of A. What it will be? Minus Na minus Na naught, because that is dNA. T2 minus T1. T2 minus T1, final time minus initial time. Time will be positive. Final minus initial. So this denominator is positive. Ultimate, we want to make it as numerator positive, because rate cannot be negative. So what we are finding? Minus dNA by dt. Rate of disappearance of A, that is the minus dNA by dt. Are you finding it or not? Bolo. So listen my point very carefully. This negative sign, you can write down, this negative sign will not use in the calculation. It will only tells us that rate is written for the reactant, because reactant will disappear, due to that I am using this negative sign. So reactant, that is minus Ri. I may be your any reactant, reactant A. If there is more than one reactant, so just I can write out as minus Ri. There is only one reactant, so I am writing it as minus Ra is equals to minus dNA by dt. Minus dNA by dt. This negative sign will be used in mathematical manipulation, mathematical calculation. This sign will be used. You cannot skip this sign. Just that is minus Ra basically shows that R stands for the rate. A stand for, that is the reactant, so I will use, that is the negative. So what I will use? Rate of formation of product. Rate of formation of product. Rate of formation of B, that is the product. So I will use plus, because that is the formation. This sign will not be used in the mathematical calculation. Plus Rb is equals to final moles Nb minus 0 divided by T minus 0. So what you can write down? You will write down it as dNB divided by dt. dNB divided by dt. dNB divided by dt. Are you finding it or not? So in this case, what I am finding, just this sign we will not use in the mathematical calculation. This sign, this negative, we will use in the mathematical calculation. So what is the definition of reaction rate? So how molecules of reactant change with time, that is called as the rate. That is called as the rate. Means how the molecules of the reactant changes with time. Suppose we are finding, try to understand, we are finding that in starting I take it as 100 mole. I take it as 100 mole of A. That time was, you can say it as time t is equals to 0 at that time. Means when I fed the reactant in the reactor. So at that time I am considering it as time is 0, mole of A, that is the 100. In next 10 second, moles becomes 10. Moles becomes 10. Remaining moles of A. What is the rate? What is the rate? You will say it as minus, in bracket 10 minus 100. So that will be 90 divided by 10. You will say it as 9 mole per second. In 1 second, 9 moles are disappearing. In 1 second, 9 moles are reacting. If I am saying it as remaining mole, that is the 0. Remaining mole is 0. Then you will say, sir, at that time rate is faster than the previous rate. Because in 1 second, 10 moles are disappearing. 10 moles of reactant A is reacting. Anurag, just wait for that. I will tell you all about the intensive extensive. So what I am finding, are you easily understanding all about the rate of disappearance of A, rate of formation of B? Now, when I am using this definition, what you are finding it as rate is extensive property. Till this point, rate is extensive property. Extensive property. Extensive, as the name suggests, you can understand. Intensive. In stand for independent of mass. Independent of mass. Extensive, that is dependent on mass. Dependent on mass. Dependent on mass. So what I will do, that is the extensive property, means it is depending on the amount of feed. If you are taking a small amount, the rate will be different. If you are taking the large amount, rate will be different. If you are taking a small amount, rate will be different. You are taking large amount, rate will be different. So at that time, what we are finding, that it is depending on the mass. So to make it extensive property, same you know, that mass divided by volume, that is the density. Density means mass, that is the extensive. Volume, that is extensive. You will take it as a small volume, its mass will be different. You are taking the larger volume, its mass will be different. You are taking that is in very small amount. You are taking any substance in a small amount, its mass is different. You are taking the amount in the large, so just, or you are taking it bulk, in bulk, its mass will be different. So means that it is depending on the mass. Mass divided by volume, extensive by extensive, rho, density, mass over volume, that is the intensive. That is the intensive. So in this case, what I will do to make it its intensive property, just I will divide with volume. Volume of what? Volume of reaction mixture. Volume of reaction mixture. So I will divide with volume of reaction mixture, that it will be your, now rate is your extensive property. Before it was the intensive property. Now it is your extensive property. It is your intensive property. Independent of mass. So now it is not depending on the amount of feed, because a small amount, so volume will be different, volume will be small. Large amount, so volume is large. Are you finding it or not? हम लोग इंटेंसिव क्यों कर रहे हैं, कोई वजह? सोएब, उसकी वजह ये है कि अगर आपने मीन्स you want to define the rate in a small vessel. Rate in a small vessel will be different as compared to rate in the large vessel. So just because in a small vessel amount of the feed is small, in large vessel amount of the feed is different. So just I am making it with independent of the mass. by dividing the volume. Now you are taking it as a small volume and a small amount of feed, same rate. Large volume, large amount of feed, same rate. So just to make it as independent from the mass, we are making it extensive property. Obviously, now what is the unit? Just try to understand. Unit is my DNA. What it is represent? It's represented as moles of disappearance of A. Moles of disappearance of A. Divide by, or you can say it as moles of A reacting. Moles of A reacting. Divide by volume of reaction mixture. Volume of reaction mixture into time. Simple, you can say it as its unit is now mole per meter cube per second. In this case, what was its unit? Mole divided by a mole of A divided by time. DNA minus DNA is what? That is the moles of A reacted. It is what? That is the moles of A reacted per unit volume per unit time. Now rate, we will consider it as intensive property, independent from mass. In previous, why it was the dependent on mass? Mole. Mole is what? Mass over molecular weight. Mass over molecular weight. So you will take it as amount of the feed, that is small. So obviously what you are finding? Mole means mass is different divided by molecular weight. So it means that that amount of the feed rate, that is depending on the amount of the feed. If I am taking it as the large, means large mass, so mass divided by molecular weight, moles will be different. Moles will be different. So in this case, rate will be different. So to make it from independent from the mass, just I will divide with volume. I will divide with volume, means rate will depend on amount of the feed. To make it independent from amount of feed, I am dividing with volume of reaction mixture. So simple, it will be your intensive property. Now it will not depend on the mass. What will be its unit now? Its unit will be mole per meter cube per second. You can say it as moles of A reacting per unit volume of reaction mixture per unit time. That is different thing. That rate is independent from size of reactor. Why we are making it intensive? Because in starting you are taking it as small, means small feed. You can say it as very few moles of A. In another condition you are taking it as very, means large moles of A. We are giving same time. We are giving same times. So what you are finding? That rate will be same. So in starting, rate is depending on the mass. We want to make it independent from the mass. So just what I am taking, I am dividing with volume. A small amount, its volume will be small. Large amount, its volume will be large. So in both of the cases, you will find out the same rate. So now there will be no tension in your mind that this rate is correct, this rate is correct. So just if you are dividing with volume, now it is independent of mass. Obviously you can say it as either this vessel, this is the rate of this reactant, rate of disappearance of this reactant. That is the rate of formation of this product. Simple. Sir, it is the moles of A reacted or reacting. अरे यार सेम ही चीज तो है. कितने मोल्स A के रिएक्ट हुए? In starting, if it is 100 at time t is equals to 0, and in next 1 second it's become 10. So that this is moles of A reacting, that is the 90. Simple. 90 per unit volume. What is the volume of reaction mixture? Per unit time. So time, that is the one. So that will be the rate. So in this way we will define the rate. And what it will tells us? You can say kinetics. Kinetics. What does it mean? It means that is the speed oblique rate of a reaction. It will tells us that is how fast or slow how fast or slow reaction will takes place. Reaction will takes place. I already told you by taking two example. When rate will be high, so obviously it will disappear fast. When rate is slow, so it will take large time to disappear till same extent. In both of the case, same extent. So reaction rate tells us how fast or slow reaction will takes place. Are you finding it or not? Nitish, you can say in this manner, okay? कि वही चीज है जैसे हम स्पेसिफिक वॉल्यूम पढ़ते हो आप, ठीक है, या स्पेसिफिक एंथैल्पी, स्पेसिफिक एंट्रोपी. So just what will take? Divide by mass. Here what we are finding? We are taking it as divide by volume. Any doubt till this point? So minus RA, that will be your minus 1 by V dNA by dt. Plus RB, what it will be? Plus RB. Rate of formation of B, that will be plus 1 by V, volume of reaction mixture, dNB divided by dt. In this case, you will write out as, here you write out as moles of A react, moles of B formed, divided by volume of reaction mixture per unit time. Volume of reaction mixture per unit time. You get this point? So now try to understand how we will define the rate. We are defining the rate, or just write down here, rate for homogeneous reaction. How we will define the rate? Rate for the homogeneous reaction. For the homogeneous reaction. So simple, you will write out as rate of disappear of component I, rate of disappear of component I, that is minus Ri, will equals to minus 1 by V dNi divided by dt. Where V is what? I am telling you again and again, volume of reaction mixture. Volume of reaction mixture. So for the homogeneous reaction, you will define the rate based on volume of reaction mixture. For heterogeneous reaction, try to understand. For heterogeneous reaction, what you will find out? In this case, may be possible that there is more than one phase, that is gas solid phase, liquid solid phase, gas solid phase, liquid solid phase. We are finding it as, because for the homogeneous reaction, simple reactant as well as product, or this reaction will occurs in a single phase. For heterogeneous reaction, reaction will occurs in more than one phase. So I am finding it as that reactant, that is in the gas phase, product is in the gas phase, but catalyst, that is in solid phase. Catalyst is in the solid phase. Reactant is in liquid phase, product is in liquid phase, but in this case we are using the catalyst is in the solid phase. So for such case, how we will define the rate? So we can define the rate, means that is the fluid solid system. We can define the rate based on mass of solid. We can define the rate based on volume of solid. Suppose reaction we are taking place, that is gas liquid, heterogeneous reaction, more than one phase. So we can define the rate based on interfacial surface area of the fluid system. Interfacial surface area of fluid system, because when heterogeneous reaction will takes place, there is more than one phase. So reaction generally occurs at the interface. So here gas liquid, more than one phase, reaction will occurs at the interface. So just to defining the rate, I am taking, so now let's see. So rate for homogeneous reaction, I am writing that is the rate of disappearance of component I minus Ri will equals to minus 1 by volume of reaction mixture dNi by dt. Get this point? Now for heterogeneous reaction, I can define rate of disappearance of component I based on mass of solid based on mass of solid based on mass of solid in fluid solid system or in fluid solid reaction, means either that is the gas solid liquid solid reaction. So how I will write it? Minus Ri prime minus 1 by W that is the mass of the solid, W that is the mass of solid. So what will be its unit? Its unit will be moles per kg of solid per unit time. Are you finding it or not? So means you can define in heterogeneous reaction, you can define the rate in various form. It is not the compulsion that you will define based on volume of reaction mixture. You can define based on mass of solid. You can define based on surface area of solid. You can define based on volume of solid. You can define based on interfacial surface area of fluid reaction system. You can define rate based on volume of the reactor. You can define the rate based on, you can say, porosity. You can define the rate based on various factors. So just you should understand, in heterogeneous reaction system we can define the rate based on various factors. Okay, so minus Ri prime, or you can say it as rate based on interfacial surface area of fluid system or interfacial surface area of fluid system or solid fluid system. So how you will define? You will define it as minus Ri, you can denote it with double prime, minus 1 by S dNi divided by dt. Are you finding it? What will its unit? Moles of A reacted per unit surface area of solid, or either per unit surface area of interface of fluid system per unit time. You can define on the behalf of minus Ri third prime based on volume of solid dNi divided by dt in fluid solid system. You can define minus Ri fourth prime. You can define based on volume of reactor. You can define based on void volume of the reactor, VO. You can write out as void volume of the reactor into dNi divided by dt. So means we have various aspects by that we can define the rate in heterogeneous reaction system. So when you will equate all the rate, what you will find out? Minus dNi by dt. So simple, that will be your minus Ri into V. What will find out? Minus Ri into V. V, that is the volume of reaction mixture. Minus dNi by dt. You will find out as minus Ri double prime into S. S is what? That is the means minus Ri into, you can write out as first W. Minus Ri prime into W. W, that is the mass of solid. That will equals to minus Ri double prime S. S, that is the external surface area for the fluid solid system. For fluid system, you can say it as interfacial surface area. That will equals to minus Ri triple prime into Vs, that is the volume of solid. You can write out as will equals to minus Ri 4 prime into Vr, that is the volume of reactor. Will equals to minus Ri 5th prime into, that is the VO, void volume of the reactor. Means in whole reactor volume, when you will subtract the volume of solid, you will find out as that is the void volume of reactor. So based on various aspects, you can define the rate. Are you getting it? So that will equals to minus dNi divided by dt. So sometimes you will find out as in your question, volume of reaction mixture is given to you, rate is given to you, and after that the same reaction that is taking place, with the help of the catalyst, and mass of the catalyst is given to us, external surface area of the solid is given to us, volume of solid that is given to us, just they can ask the rate. So means you can equate. After that, if you are equating, that is minus Ri into V will equals to minus Ri first prime into W. So means 3 parameter that will given to you, you can easily find out as one of the unknown. So either minus Ri W minus Ri prime into W will equals to minus Ri double prime into S. So in this case, when you will equate, so 3 quantity will be known to you, you will find out as the unknown. Simple. So what we are finding, definition of the rate. If anyone is asking you that write down the definition of rate, so you will tell that minus Ri, rate of disappearance of component I, that will equals to minus dni divided by dt into V, or you can write out as minus 1 by V. Just you will not write down as minus dCA by dt. Why you will not write down minus dCA by dt? Because may be possible during the reaction, this volume of reaction mixture, it may be constant, may be possible that it is changing. When it is constant, then you will write down it as minus dni divided by V divided by dt, that it will be your minus dCA by dt. So that is for constant volume reaction mixture or reaction system. For constant volume reaction system. So in very starting, when you do not know that it is the constant volume reaction system, volume of the reaction mixture is constant, or volume of reaction mixture is not constant. So just how you can write down it as, sir, minus dc minus Ri will equals to minus dCi divided by dt. How it is possible? Tell me. Minus dCi divided by dt. So simple. If anyone asks all about the rate, you will tell this expression minus Ri is equals to minus 1 by V dni by dt. Are you getting it? Just you will not say directly that minus dCi by dt until and unless it is not mentioned the volume of the reaction mixture during the reaction is constant. Otherwise, for the variable volume reaction system, I will tell you how you will define the rate. VO, that is the void volume. W is the kg of solid, that is the mass of solid. तो catalyst को भी change कर दोगे क्या? Catalyst that will not participate in the reaction. Volume of the catalyst that will be fixed. अच्छा, solid reactant के base पर आप reaction rate define कर दोगे. That is the change variable. Simple यार, वो change होगा आपका time के साथ में. Mauria, W, that is the mass of the solid. Mass of the solid means you can say that is the mass of catalyst. V is volume of reaction mixture. So in very starting, just I do not define that rate of disappearance of A is how the concentration is changing with respect to time. Or you can say that just I am writing it as that is the minus difference in concentration of A divided by difference in time. That is not the correct definition. Minus Ra, I am writing it as first of all in terms of mole. Means change in mole per change in time. That is the extensive property. I am making it intensive. So I will write down it as minus 1 by V dni divided by dt. If it is constant volume reaction system, then what I will write? Then you can define this rate, that it will equals to minus change in concentration. Either you can use that is the big bracket, change in concentration of A divided by del T. You can use this definition. Either you can write out as minus del Ca divided by that is del T. That will be the definition. Are you finding it or not? Interfacial that A means S is interfacial surface area, or you can say that is the external surface area of the solid. Are you finding this point? How you will define the rate? किसी को कोई doubt? How you will write the definition for the homogeneous reaction system, or homogeneous reaction and heterogeneous reaction? Now after that, put the heading that is limiting reactant. Limiting reactant. Limiting reactant. Try to understand. Suppose I am taking any reaction. I am taking any reaction. That is N2, or write down it as A in the gas phase, B in the gas phase, gives C in the gas phase. At time t is equals to 0, we have the 10 mole of reactant A, or just you can write down as 2A plus B gives C. Okay. In starting I have 10 moles of reactant A, 30 moles of reactant B, 30 moles of reactant B, 10 moles of reactant A, 30 moles of reactant B, and C at time t is equals to 0, that is moles of product C are 0. Now at any time t, try to understand, at time t1 2 moles of A reacted, remaining mole that is the 8 moles. Now tell me how many moles of B will react, how many moles of B will react, and what are the remaining moles of B? Bolo. So when 2 moles of A react, 1 mole of B will react. 1 mole of B will react. Remaining mole you will find out as 29 moles. How many moles of C will formed? That is simple, 1 mole. 1 mole. Are you finding it or not? At another time, remaining moles of A, that is the 6 moles. 6 moles. So at time t1, 8 moles, B contains 29 moles, C contains 1 mole. After that, in the next time, again 2 moles of A disappear. What we are finding? So when 2 moles disappear, the moles of B will disappear, that will be the 1. Because 2 moles say, what it is represent? Stoichiometric coefficient. Represent the, you can say, number of moles. Represent the number of atoms, number of molecules. In case of the gas phase reaction, it represents, that is the pressure. It represents the volume, but it does not represent the mass. So 2 moles of A reacted. So the moles of B reacted will be 1. Remaining moles will be 28 moles. And after that, C will be formed. The moles of C will formed 2 moles. So at that time, what you are finding, when A will be complete converted, 0 moles. So the remaining moles of B will be 25 moles, and moles of C will be formed 5 moles. 5 moles. In this case, what we are finding? We are finding the limiting reactant. Limiting reactant means the reactant which consumed first in the reaction. That is called as limiting reactant. So here reactant A is the limiting reactant. You can write down as the reactant limiting. Limiting means the reactant that consumed first. Okay, that is called as limiting reactant. So A is limiting reactant. B, I will say it as it is in excess, or it is the excess reactant. Why? Because A gets fully converted. After that, we have some moles of B, that is the 25 moles. So what I am finding, limiting means limiting reactant, the reactant which gets consumed first in the reaction is called as limiting reactant. So here A is limiting reactant. Reactant B, that is the excess reactant. Are you getting it? Bolo. Now just try to understand. If I am taking same reaction, 2A plus B gives C. At time t is equals to 0, 20 moles of A, 20 moles of B. So at any time t, if A is completely consumed, becomes 0 mole, 0. Completely consumed. B, what you are finding? B, that will be completely consumed. C will formed 10 moles. 10 moles. C will consumed 10 moles. Are you finding it or not? So here I will say neither A nor B is the limiting reactant, or you can say it as both reactant A and B are the limiting reactant because they consumed at the same time. So you will say both A and B are limiting reactant, or either you can say it as none of the reactant is limiting reactant. Are you finding this point or not? Bolo. So you know very well all about the limiting and excess. It is very simple to analyze. Now, at the same time, this term I will discuss later all about the conversion or fractional conversion. So that is defined for which reactant? Fractional conversion. This is defined for which reactant? Bolo. So just correct it. That is the B is 10 moles. Okay. Now tell me which conversion that is defined for. Conversion, percentage conversion, or you can say it as, if it is only mentioned conversion, so it means it is the fractional conversion. It is defined for limiting reactant. Conversion I will define later, but before that just try to understand. Conversion is defined for the limiting reactant. Sir, why is not defined for the excess? My dear students, in this case, what you are finding, you have the 10 moles, now remaining moles is 20. Remaining moles is 20. It gets consumed first, no reaction will take place. No reaction will take place. So when it is not get consumed, okay, means it want to consume, but this reaction is not possible without A. So how you will define the conversion for reactant B? First of all, you will find out which reactant is limiting reactant. Then you will define the conversion for that reactant. Try to understand. After that, write down next one, power law kinetics. Power law kinetics. Try to understand. Any reaction is taking place. A plus B, capital B gives C plus D, capital D. You know very well, A, capital B, capital C, capital D are called as chemical species, and small a, small b, small c, small d, these are called as stoichiometric coefficient. These are called as stoichiometric coefficient. If I want to write down rate of disappearance of A, rate of disappearance of A, rate of disappearance of A. So power law kinetics tells us that it can be written as, or means minus RA, that will be directly proportional to concentration of A to the power alpha, concentration of B to the power beta. Means just multiplication of the concentration of reactant A multiply concentration of reactant B to the exponent, concentration to the exponent. That is the alpha, that is the beta. So this minus RA, which you can write down it as, just you will remove the proportionality sign, you will take the proportionality constant, that is the K. Ca to the power alpha, Cb to the power, that is the beta. K is what? That is called as rate constant. That is called as rate constant. Rate constant. Rate constant. Or it is called as specific reaction rate. Specific reaction rate. Ca is what? That is the concentration of A. You know very well. Concentration of A. Cb is what? That is the concentration of B. Concentration of B. So minus Ra, which you already defined, minus 1 by V dNA by dt. So what it will be? Rate will be directly proportional to multiplication of the concentration for different reactant and the exponents, means the, you can say it as the power on the concentration, that is the A, means that is not the A, that is the alpha, that is the beta. Alpha is called as order with respect to of reaction with respect to reactant A, with respect to reactant A, and it is not necessary that alpha will equals to small a. It is not necessary that alpha will equals to small a. Same beta. Beta is called as order of reaction with respect to reactant B, and it is not necessary that beta will equals to small b, means stoichiometric coefficient b. But from this power law kinetics, I can define that overall order of reaction. Overall order of reaction, not with reference to reactant A or reactant B. What it will be? Overall order of reaction. I am denoting it with n. That will be alpha plus beta. So that is not the alpha plus beta. If there is more than one reactant, so just alpha plus beta plus gamma plus dot dot dot. That is called as power law model. Mayank, I did not define anything. Either it is the elementary or non-elementary. Just I told you all about the power law kinetics. Power law kinetics tells us that rate of disappearance of reactant A can be written as multiplication, the multiplication of the concentration of reactant, means Ca, its power, that is the alpha. It is not necessarily that it will equals to the A. It may be equal to A, it may not be equal to A. Beta, that it is equal to B or not. So it is not necessary, but rate that will be written in this form. That is nothing but that is the power law model. That is the general rate law. Okay. In another way, you can write down minus Ri, rate of disappearance of reactant I, will equals to K, rate constant or specific reaction rate. Just what you will use? You will use that is the multiplication. I is equals to A, means it may be reactant A, reactant B, reactant C, reactant D. C, or just you can write out as that is I, Ci to the power, that is the alpha I. Ci to the power alpha I. Rate of disappearance of reactant I is directly proportional to multiplication of the concentration of component I, multiplication of concentration to its exponent for different component. Are you finding it or not? Try to understand this point. I will tell you each and everything, just wait for that. Rate, that is the experiment determined quantity. Okay, we will define on the, means when I will define the elementary and non-elementary reaction. So just that is all about this portion, that is the chemical kinetics and all about the reaction mechanism. So I will discuss each and every term in detail. Just wait for that. Power law kinetics, what it tells us, that rate of disappearance of any component I, that is directly proportional to multiplication of the concentration to the exponent for different component. Are you finding it or not? So either you can say I, that is for the component A. So concentration of component A to the power alpha A. Alpha, that is the order of reaction with respect to reactant A. Alpha B, that is the order of reaction with respect to reactant B. Overall order of the reaction, that is the N. So that is your power law model. Now try to understand. If I am taking the elementary reaction, try to understand that is the elementary reaction. Reaction is A plus B gives C plus D. And I am saying this is the elementary reaction. So what you can write down? Rate of disappearance of A. So in this case, how you will write down? You will write down as that rate expression that will be corresponds to the stoichiometric coefficients, corresponds to the stoichiometry. You can say it as Ca to the power A, Cb to the power B, Cb to the power B. Now just understand. First of all, you should know rate is experimental determined quantity. Rate is experimental determined quantity. Rate is experimental determined quantity. Just you cannot say, sir, for this reaction, this is the rate. For another reaction, this will be the rate. You cannot predict, you cannot find, because rate is the experimental determined quantity. So in the laboratory, what we will do? Just either that is your batch reactor, okay, or either it is your continuous reactor. What generally we will do? We will just fed the reactant. After that, at different time, we will take the sample and we will analyze that what is the concentration of A, what is the concentration of B. At different times, so we have the various data. Then by integral method or by differential method or either by excessive method, we have various method to find out that what is the order of the reaction. Rate is experimental determined quantity. Then what we'll find out? With the help of experiments, we will understand how the rate is depending on the concentration of different reactor. So we are finding it as minus RA, that is directly proportional to concentration of A to the power A, concentration of B to the power B. So when I am finding in this manner, so I will say this is the elementary reaction and it is the elementary kinetics. Elementary kinetics or elementary rate law, you can say. Elementary rate law. Try to understand. Just try to understand. So what we are finding from the experiments? What we find? We find that for the reaction, if we are finding the rate expression that is corresponds to the stoichiometric coefficient. So you will find out the rate. Just try to understand, otherwise you will be confused. Okay, rate is experimental determined quantity. So for any reaction you will find out the rate. Okay, so for this reaction you find out the rate, and this is your rate expression. Then I will suggest different model. Try to understand. I will suggest different models, and I am finding it as this reaction is taking place in single step. Then after that, what I will say? I will say this reaction is elementary reaction. After that, what I did? I just remove out this expression. Then I am saying, if this reaction is elementary reaction, what will be the rate expression? Then you can tell, because this reaction is the elementary reaction, so its rate expression will be K Ca to the power A, Cb to the power B. Otherwise you cannot tell that for this reaction what will be the rate expression. For this reaction, rate expression, that is the experimental determined quantity. So I will find out, later I will tell you how you will find out. You will find out the rate expression by taking the sample, or by when this reaction will react. After that we will take the sample, then we'll find out the rate expression. In the form of power law model, power law kinetics. After that, I will suggest the model. I find out as this reaction is taking place, this reaction is completing in a single step. There is no intermediate form and all these things. So what I will say, this reaction is elementary reaction. Now, for if it is, then what I am saying, this reaction is elementary reaction, and I do not know the rate expression, so then it will be the rate expression. Now, just try to understand. Now, try to understand. Try to understand. H2 plus I2 gives 2Hi. H2 plus I2 gives 2Hi. 2Hi. Rate of disappearance of hydrogen, that is K. Concentration of H2, concentration of I2. This is the rate. This is the rate, which is elementary rate law. Elementary rate law. Elementary rate law. This is the reaction I am taking place, means from the experiment I find out as it is the rate expression. It is the rate expression. This rate, simple, I observe the stoichiometry. So rate is as per the stoichiometry. What I will say? Reaction is elementary reaction. What I will say? Reaction is elementary reaction. From the rate expression, can I say reaction is elementary reaction? Although I am finding it as elementary rate law, elementary rate expression. So just try to understand. Try to understand. If I am saying it as elementary reaction, or I am saying it as elementary rate law, elementary rate law, elementary rate law. So for this reaction, again understand, this is the reaction, this is the rate expression we find out from the experiment, because rate is experimental determined quantity. You find the rate. Then rate is by the power law model, kCa to the power a, cb to the power b, small b. Then I will go for this reaction. I suggest a different type of model. I find it as this reaction is completing in a single step. This reaction is completing in a single step. Then I am saying it as it is the elementary reaction. Now if I erase this rate expression, this reaction is elementary reaction, then I can write down that that will be the rate law. So if reaction is elementary reaction, its rate law will be the elementary rate law, But if I am finding the elementary rate law, it does not suggest that reaction will be elementary, because this, for example, this is non-elementary reaction. This is non-elementary reaction. What does it mean? Non-elementary reaction. What does it mean? What does it mean? It means, as you say, as per your definition, that sir, elementary reaction are those reaction rate law is corresponding to the stoichiometry. Non-elementary rate law, that is not corresponding to the stoichiometry. For this reaction I am finding it as per the corresponding the stoichiometry. But after that, what I am saying, that reaction is non-elementary reaction. So it means reaction is elementary reaction, rate will be experimentally elementary rate law. But if the rate is elementary rate law, you cannot say reaction will be elementary reaction. This elementary rate law you can find out for the non-elementary reaction. So just it is not a single example. You will find out as 2NO plus O2 gives 2NO2. What you will find out as minus RNO, rate of disappearance of nitric oxide, that is K, concentration of NO square, concentration of O2. We are finding it as elementary rate law, but after that this reaction is non-elementary reaction. So what we are finding, that non-elementary reaction, it will not complete in a single step. It will not complete in a single step. So either it will follow non-chain reaction mechanism or either chain reaction mechanism. Means in this case, intermediate will be formed. Intermediate, either it may be the free radicals, it may be the ions, it may be the polar substance, it may be the molecule, it may be the transition complex or activated complex. But this reaction will not occur in a single step. This reaction occurs in many steps. Means either in chain reaction or non-chain reaction. So then for this reaction, I will suggest different model. I will suggest different model. So in various models, one model that will be accurate, that will be the rate expression. No doubt that will be the rate expression. But this reaction will not occur in a single step. When you will add up all the reaction, then it will be your final reaction. So that is just very basic difference in between elementary and non-elementary. After that in detail I will tell you in the next class. हो भी सकता है सर एलिमेंट्री है, ठीक है जी, आपने बोल दिया एलिमेंट्री हो सकता है, ठीक है. So what we are finding, this reaction that is not occurring in a single step. Obviously non-elementary reaction contains multiple steps and all the steps are elementary. So it will not occur in a single step. Either it will follow the non-chain reaction mechanism or chain reaction mechanism. Are you finding it or not? So means just try to understand, if reaction is elementary reaction, you can write down the rate law. How you can write down? Just you cannot write down as that it is the elementary reaction. First you find that is the experimental determined quantity, what is the rate law. You see this reaction will complete in a single step. Then you erase this rate expression. You are saying it as this reaction is elementary reaction, so directly I can write down the rate law. If this is the reaction, from the experiment I find out as it is the rate law, elementary rate law. But this reaction is not completing in a single step. So what I will say, non-elementary reaction. But for non-elementary reaction, you can find out the elementary rate law. Try to understand. Elementary reaction है, तब आप rate law लिख सकते हैं. But अगर if your rate law is elementary rate law, you cannot say that reaction is surely elementary reaction. It may be non-elementary too. हाँ, Sukant, obviously Sahil, by analyzing the elementary rate law, you can't say that reaction is elementary or reaction is non-elementary. Rate law कैसे find out करोगे? That is the experimental determined quantity. Experimental determined quantity है, अपने मन से कुछ नहीं लिख सकते हैं. Okay, so further I will discuss in the next class in detail. That is for the today class. अनुराग उसको बताएंगे, उसमें जो आपका एक्टिवेटेड कॉम्प्लेक्स रहेगा, जो भी इंटरमीडिएट रहेगा ना, इंटरमीडिएट मीन्स वी विल टेक इट एज स्यूडो स्टेडी स्टेट हाइपोथेसिस और स्यूडो स्टेडी स्टेट अप्रोक्सीमेशन. वी अज्यूम दैट the concentration of intermediate which is highly reactive but that is not stable, so its concentration is so low that we cannot measure it. Its rate will be zero. On the behalf of that we will find out the rate expression. Thank you very much.